Good morning, everyone. So we're going to have our DSG seminar today. And it's wonderful that we have our speaker, Xiaokui Xiao from National University of Singapore. And Xiaokui is our Dean's Chair Associate Professor at the School of Computing. And his research work focuses on data management with special interest in data privacy and algorithms for large data. He has published a lot of amazing work on those topics. And it's our pleasure to have him today to talk about his work on efficient network embedding for large graphs, right? And especially now it's nighttime for Xiaokui. We really appreciate that. Okay, feel free to start. Yeah, we're very looking forward to the talk.
Thanks for the kind introduction. So the topic of my talk today is about network embedding. And the problem definition is pretty simple. So we have a graph with some nodes and edges. And what we want to do is to map each node in the graph into a fixed dimensional real vector. And the purpose of doing this mapping is to obtain such embedding vector for each node so that we can use them for some analytical tasks on graphs. For example, we can take the embedding of each node and feed it to a classifier, and then ask the classifier to tell us the label of the node. So for instance, if the input graph is a social network, then this classifier may tell us whether the user corresponding to a node is a real user or a fake one. As another example, if the input graph is a transaction graph where each node is a transaction, then the classifier may tell us whether the transaction is a legitimate transaction or a fraudulent one. As another example, let's say we have a social network and we want to know whether two nodes are likely to get connected in the future. Then we may pass the embedding vector of those two nodes to a classifier and then ask the classifiers to predict the likelihood of having a connection between these two nodes in the future. And this could have applications in social recommendation because if we know that two nodes are likely to get connected in the future, then we may introduce them to each other as a recommendation of friends. So there has been a huge number of solutions for deriving network embeddings from graphs. But one thing that we observed is that most of the solutions for network embedding would incur significant time or space overhead. And in many cases, this is due to some expensive training of neural networks. So this motivated us to conduct a study on efficient methods for network embedding so as to strike a better balance between the quality of the embedding and the space and time overhead. So in what follows, I'm going to talk about two of our recent work on efficient algorithms for network embedding. And I'm going to start from the case when the input graph does not have any attributes. So here I'm assuming that the input graph has only nodes and edges, and there's no attributes associated with any nodes or edge. So in this case, what the embedding needs to capture is only the graph topology. And for such a setting, the classic solution is deep walk, which was proposed back in 2014. The basic idea of deep walk is as follows. It uses random walks to identify nodes that are close to each other. And then you would use a neural network to train the embeddings of the nodes, such that if two nodes are close to each other in some random walks, then their embedding vectors would have a large inner product. So this is kind of saying that the direction of their embeddings would be sort of similar. More specifically, the way that deep walk generates random walk is as follows. You first pick an arbitrary node in the input graph and then perform a relatively long walk in the graph. And let's say this is the sequence of nodes that we encounter during this relatively long random walk. Then what deep walk would do is to slide a window of constant size over this node sequence to identify those pair of nodes that are within a constant hops away from each other. So for each such pair of nodes, UV is going to use it as a training sample. So it's going to train the embedding in such a way that the inner product of the embeddings of U and V would tend to be large. And during this training process, whenever deep walk needs more sample, you just repeat this sample of random walk and then identification of node pairs and so on and so forth. And in terms of the training of the embeddings, deep walk would use a standard stochastic algorithm to do it. So you will initialize the embedding of each node with some random values. And then you iterate through the training samples, which will be just some node pairs, and gradually revise the embeddings until the embeddings converge. In particular, the training of the embeddings is based on a certain loss function. The loss function would take a look at each node pair in the training sample and check the inner product of those node pairs embeddings. So if the inner product is large, then the loss for this particular node pair is considered small. Otherwise, the loss would have a large value for this node pair. And what deep walk would do is to train a neural network to minimize the sum of this loss value for the training samples in the training set. So the idea of this deep walk algorithm is pretty intuitive, but one of the issues of the algorithm is that the training cost is significant because we need to start with some random initial value for the embeddings, and then we need to iterate through a lot of training samples and gradually refine those embeddings to make them good. So after deep walk, there has been a lot of subsequent studies on neural network-based methods for network embedding, and they improve deep walk in two aspects. So they have better ways to generate the training samples, and some of them use more advanced neural network structures. However, the efficiency issues still remain. So the training process for these algorithms is still very costly because they still need to start with some random value and they still need to go through a lot of training samples. As a consequence, it's quite difficult to scale them to large graphs unless you have some huge computation power with a lot of CPUs and GPUs and memory. We would like to approach this problem from another angle. So we would like to avoid the usage of random walk, usage of neural networks in the training of embeddings, but we still want to derive some embeddings that are of high quality. So the way that we'll do it is to first revisit the ideas behind deep walk and try to borrow some idea from it. And then I'll talk about how we construct our embedding. So intuitively, what deep walk was doing at a high level is as follows. It first models the affinity or the similarity between nodes based on their proximities in random walks. So this affinity measure is not explicitly defined, but is implicitly encapsulated in the loss function used by deep walk. And then based on this implicit affinity, what deep walk did is to train the embedding in such a way that whenever two nodes have a high affinity, their embeddings would have a large inner product. So in some sense, the inner product of those embeddings would be an approximation of the two nodes affinity value. So if we look at it from this angle, then deep walk is essentially doing a matrix factorization. In particular, we can imagine that there is an n by n affinity matrix, where n is the number of nodes in the graph, and each entry in this matrix is just the affinity value between a node pair. Okay, so it's the affinity value that is implicitly captured by deep walk. And then if you think about the embedding that deep walk generates for each node, you can think of it as something that forms an embedding matrix, where each row corresponds to the embedding vector of that node. In that case, what deep walk was trying to do is to make sure that when you take this embedding matrix multiplied with its own transpose, then the end result would be an n by n matrix that approximates the implicit affinity matrix. So at a high level, this is what deep walk was doing. Now, if we want to do the same thing without using a neural network, what can we do? Intuitively, the first thing that we can do is to explicitly define an affinity measure so that we can construct this affinity matrix without using a neural network. And then once we have this affinity matrix, we can just apply some existing matrix factorization algorithm to obtain the m by k embedding matrix on the left-hand side here. So this is what we're going to do in our approach. But to make it work, there are at least two problems that we need to address. The first one is, which affinity measure should we use? The second is, after we define our affinity measure, how can we derive the embedding matrix without materializing the n by n affinity matrix? We need to avoid this materialization because when the number of nodes in the graph is large, the number of entries in this n by n matrix is going to be prohibitive. We can't just materialize it. So we have to have a way to derive the embedding matrix without materializing the affinity matrix. So in what follows, I'm going to talk about how we address these two problems. And the basic idea is that we will use something called personalized PageRank as the affinity matrix between the nodes. And then we're going to incrementally factorize the affinity matrix without materializing it. So the idea is that we're going to start from some small components of the affinity matrix, and then we're going to factorize those small components. And then we're going to use those factorized components to incrementally build up some other components so that at the end of the day, we can obtain a factorization of the affinity matrix without materializing it. Okay, so let me first explain what a personalized PageRank is. So given a graph, let's say we have a node U, and let's say we start a random walk from this node U. And in this walk, let's assume that at each step, we're going to stop with a constant probability alpha. And a typical setting for alpha would be something like 0.15. Okay, so we just walk and walk, and at some point, we're going to stop. Then the probability that we start from a node U and eventually stop in a node V is defined as a personalized PageRank from U to V. So that is, if you start from U and you take a random walk in the vicinity and you randomly stop somewhere, then the probability that you stopped at a particular node V is a personalized PageRank from U to V. This affinity measure is quite intuitive because intuitively, if you have a lot of connections from U to V, then the probability of starting from U and starting from at V would be relatively large. And that sort of indicates that U and V have a high affinity. So personalized PageRank has actually been used in quite a few prominent applications in practice. For instance, Twitter used personalized PageRank to recommend accounts for users to follow in a service that they called Who to Follow, or WTF. As another example, Pinterest used personalized PageRank to recommend images and videos to users. So it's fair to say that personalized PageRank has a proven track record as an affinity matrix. So we would like to compute the personalized PageRank between different nodes, and then we would like to use those personalized PageRanks as our affinity measure to construct embeddings. But then the question is, how can we actually compute the personalized PageRank from one node to another? There are quite a few different ways to do it. And one of the most simple way is to utilize the transaction matrix of the input graph. And by the transaction matrix, what I mean is an n by n matrix where each column corresponds to a node in the graph, and each entry corresponds to an edge in the graph. And the value of the entry will be equal to 1 over the degree of the node where the edge starts from. So for instance, this entry corresponds to this edge here from node V1 to V2. And its value is 1 over 3 because this edge starts from node V1, and V1 has 3 edges going out. Same for the other entries in this transaction matrix. So why do I say that the personalized PageRank matrix can be computed from the transaction matrix? The idea is as follows. The personalized PageRank matrix can be expressed as a sum of alpha times the identity matrix plus a geometric sequence involving the transaction information P. So let me explain. So let's first think about the events that we start a random walk and we just stop right at the very beginning. Okay, so that event would happen with the probability alpha, right? That is the probability of stopping at each step. And when we stop right at the very beginning, the end point of the random walk is going to be the same as the starting point of the random walk. So this event can be modeled using this matrix here, which basically says that if we stop right at the very beginning, then the starting point will be the same as the end point. And this kind of event happens with the probability alpha. Okay, so that's what this part means. Now let's consider the events that we start from a node and we stop right at the first step. Apparently, this event would occur with the probability alpha times 1 minus alpha. And if you think about the distribution of the endpoint of the random walk in that case, you can see that it's exactly captured by the transaction matrix, because the transaction matrix exactly tells us where we're going to end up with if we start a random walk and stop right at the first step. Okay, so this part corresponds to the case when we have a one-step random walk. Similarly, for this part, it corresponds to the case when we have a two-step random walk, because the probability of having a two-step random walk is alpha times 1 minus alpha squared. And the distribution of our endpoint can be captured by p to the power of 2, because that's exactly where we're going to end up with if we take a two-step walk starting from each node, so on and so forth. Right? So that's one way to compute the personalized PageRank matrix. So it involves alpha times the identity matrix plus the sum of a geometric sequence involving P. And observe that in this geometric sequence, there is this constant 1 minus alpha to the power of I. So apparently it decreases exponentially when I increases. So we can truncate the tail of this geometric sequence without losing too much accuracy. In particular, if alpha is set to 0.15, then retaining only the first 20 terms of this sequence would usually give a good enough approximation. So that is how we can compute the personalized PageRank matrix. But there is a problem. We can't just use it in our approach because this power of P can still be a very dense matrix that requires prohibitive space. And the reason is that if you imagine that you start from a node in a graph and you take I step out, then chances are that after I step, you can already reach almost everything in a graph, especially when the graph has a small diameter, such as a social network. So even though we can compute the personalized PageRank matrix in this way, we can't directly use this approach. But if you think about it, at the end of the day, what we want is to obtain a factorization of the personalized PageRank matrix so that we can have some embeddings. So that would mean we do not necessarily need to materialize the power of P. So as long as we can somehow factorize it, we should be okay. So that motivates us to use the factorization of this transaction matrix to reduce space and time overheads. So the idea is as follows. So given the transaction matrix P, what we're going to do is to first factorize it using some existing algorithm to obtain two n by k matrix, where k is a small constant. And then, so let's say the two factorized matrix would be x1 and y. Okay. And then what we're going to do is to take the matrix on the left-hand side here, multiply it with the transaction matrix P. So why do we do that? Well, if you think about it, the result of this multiplication will still be an n by k matrix, so it will not take up too much space. And if you combine this n by k matrix with the matrix y here, then you essentially have a factorization of the second power of P. Why is that? The reason is that the combination of y and x1 here is an approximation of the transaction matrix. So if you multiply P on the left-hand side, then you have the second power of p. In other words, by utilizing the initial factorization of p, we can obtain a factorization of p to the power of 2 without materializing p to the power of 2. Okay. Similarly, if you take this n by k result here and multiply it again with the transaction matrix P, then you can combine the result, which is again an n by k matrix, with y to obtain a factorization of the third power of P. Okay, and we can carry on with this. And at the end of the day, we can just factorize any power of P without paying the n squared space overhead. Furthermore, the factorization that we have all share the same right matrix Y. And this is a nice property that we can utilize in the construction of our network embeddings. In particular, previously we were saying that the personalized page-end matrix can be expressed as a sum of alpha times the identity matrix and a geometric sequence of P. And we mentioned that this transaction matrix P can be factorized into x1 times y. Then we can multiply the matrix x1 here to implicitly obtain a factorization of the second power P, and so on and so forth, right? Now let's consider the sum of this geometric sequence on the left-hand side. To compute this sum, what we can do is to first take a weighted sum of the n by k matrix that we have here. Okay, it's all n by k matrix, and the weight of the matrix would be just these terms here. So we compute a weighted sum, and then we can just multiply the weighted sum with this matrix Y. And the end result will be an approximation of the weighted of the sum of this geometric sequence on the left-hand side. So this motivates us to construct our embedding as follows. So we take the transaction matrix, we factorize it using an efficient existing algorithm, and then we recursively multiply the left-hand side with P to obtain a series of n by k matrix. And then we take a weighted sum of those n by k matrix, and we denote it as x. Okay. And then we combine it with the right matrix Y here. And there we have our embedding matrix. So in other words, we construct our embedding matrix X and Y such that their multiplication would approximate the geometric sequence in the approximation of the personalized page-end matrix. Apparently, we are omitting this term alpha times the identity matrix, but that's okay because this term only concerns the affinity from one node to itself. So usually in applications, we don't care too much about the affinity of one node to itself. We only care about the affinity from one node to another. That's why this approximation is usually good enough. One thing that I should mention here is that since we are using this kind of factorization approach to construct our embedding, the two embedding matrices that we have are usually not the same. As a consequence, each node will have one embedding vector in the first matrix X and another embedding vector in another matrix Y. So what we're going to do is to take these two embedding vectors, concatenate them together, and use it as the embedding vector for the node. Okay, so in our paper, we also have some additional optimization in which we rescale each node's embedding to have better performance for link prediction. So the intention here is that we're going to evaluate the importance of each node in the graph. And then for those nodes that are more important, we're going to multiply its embedding with a certain constant factor. I'll omit the details here, but the main purpose of doing so is to have better performance for link prediction, and you see in the experiment. So now I'm going to talk about some experimental results. In our experiment, we use a variety of data sets with up to 65 million nodes and 1.8 billion edges. And we test quite a number of methods in our experiment. So we have two variants of our methods. The first one is called NRP, which is our method with the rescaling optimization that I just mentioned. And the other variant is called approximate PPR, which does not have any rescaling and just use the approximation of personalized PageRank for the embedding purposes. And we compared these two variants of our method with 18 existing methods. 10 of them utilizes neural networks, while the other 8 are based on factorizations or some other approaches. So in our experiments, the default embedding dimensionality is 128. And for our approach, this will mean that each of our embedding matrix will have a default size of n by 64, okay, because we need to concatenate the embedding from the two different embedding matrices. And all of our experiments are conducted using just a single CPU thread because not all of the methods in the experiments have multi-thread or GPU implementation. Our first set of experiments focuses on link prediction. So for this task, we'll first randomly remove 30% edges from the input graph. And then we're going to construct the embeddings using the modified graph with some edges removed. After that, we'll use the embedding to predict which edge should have been in the graph. For this purpose, we construct a testing set that contains the 30% edges that are removed, as well as an equal number of edges that were not initially in the input graph. And the accuracy measure in this case is area under the curve. And the higher the AUC is, the better the performance it is. So this is the experiments that we have on our data set. There are a lot of lines here, but one thing that you can observe is that this approach with red lines and squares consistently achieve the best performance, regardless of the dataset use or the dimensionality of the embedding. And that is NRP, which is our method with the rescaling optimization on each node. And as I mentioned before, the rescaling really helped the performance of link prediction. If we removed the rescaling optimization, then we would have this approximate PPR approach, and its performance for link prediction is not as good, especially on some of the data sets such as Friendster or T-Weibo. And if you look at the other existing methods, you can see that there are a few methods that offers performance that is not too far away from our approach. But as we increase the size of the data sets, those methods just disappear from the graph. And that's because they either run out of memory on our machine, or they require more than 7 days to finish the construction of the network embedding. In particular, on the largest two graphs that we have, there are only 2 existing methods that can process the embedded construction in reasonable time. And they are RANNE and PBG. But one thing that you can notice is that their link prediction performance is much worse than our method. In our second set of experiments, we focus on node classification. So for this experiment, we construct embeddings from the input graph G, and we use X% of the node labels as well as the embeddings of those nodes to train a classifier. So the percentage of the node label used varies from 10% to 90%. And then we'll use the remaining 1 minus X% of the node labels for testing purposes. And the accuracy measure in this case is F1 score. And these are the results that we have for node classification. So we do not have any results from the largest 2 graphs because on those 2 graphs, we do not have any ground truth label. So we use the small graphs only in this case. And one thing that you can observe is that on the dataset Wiki and the dataset T-Weibo, the best performing methods is the 2 variants of our methods. Meanwhile, on the other 2 datasets, Block Catalog and YouTube, we are no longer the best performing one. We are only the second best. So there is another approach called ProNE that outperforms us on those two datasets. But ProNE was unable to produce any embedding for T-Wave board because it ran out of memory. So it's fair to say that our approach provides one of the best performance on this experiment while offering better scalability than the only method that beats us on YouTube and block catalog. And in the last set of experiments, we focus on efficiency. So we vary the dimensionality of the embedding, and we measure the running time of each method. So there are a lot of lines that we have here, but you can see that roughly speaking, the methods can be divided into two categories. The first category incurred significant computation costs even on a small graphs like Wiki. And many of those methods are based on neural networks. And among those relatively efficient methods, many will stop appear as we increase the size of the data set because they either incur too much overhead on those graphs or run out of memory. And as we mentioned before, the only two existing approaches that can scale to large graphs like we did is PBG and RNNE. PBG is still much more expensive than our approach in terms of efficiency, whereas RNNE is at least 10 times faster than us. But these two approaches do not have very good performance in terms of link prediction and node classification. Okay, but of course, this set of experiments was based on just a single CPU thread. A natural question would be, what's going to happen if we allow those solutions with parallel implementations to use more computation power? To answer this question, we extract some performance numbers from the existing work that propose parallel solutions, and we have a qualitative comparison with those numbers. So PBG, which was proposed in SysML, has reported a runtime of 8 hours on this Twitter graph using 8 machines with 320 CPU threads in total. In contrast, using just one CPU thread, we can finish processing Twitter in less than 4 hours. On the largest graph that we have, which is Friendster, there is a WWW paper that presents a parallel solution. And when it uses 24 CPU threads and 4 GPUs, you can finish processing in 20 hours. In contrast, we need less than 7 hours to finish processing the same graph using one CPU thread. More recently, there is a solution that uses 96 CPU threads and 18 GPUs, and it was able to finish processing this graph in just 1 hour. So this actually points an interesting future work direction for us. That is, whether it's possible for us to use more computation power to significantly reduce the running time of our current approach. So that is how our solution for non-attributed graph works. Next, I'm going to briefly talk about our solution for attributed graphs. So for this case, we assume that in the input graph, each node has some attributes from a certain set R. So for instance, it can be a social network where each user has some attributes such as gender or the company that they work for, and so on and so forth. Or it can be a citation network where each paper will have some attribute that indicates which topic the paper is about. And following the standard assumption in the literature, we assume that for any node U and any attribute R that this node has, there is a weight that indicates the strength of association between these two. For instance, if it's a citation network, then the weight for the node pair for a paper and an attribute, let's say data mining, could be something that indicates how purely the paper is about data mining. And our objective here is to map each node U to an embedding vector and also map each attribute to an embedding vector so that we can perform some analytical tasks using the vectors. So for this problem, our basic idea is to stick to personalized PageRank and matrix factorization because they work for us for the case of non-attributed graph. So we would like to extend the solution to tackle attributed graphs too. And by using personalized PageRank and matrix factorization, we can avoid the usage of neural network, and that could reduce the computation cost. But there are several challenges that we need to address here. First, now we need to tackle two types of affinities in this case. We have the affinity between nodes, and then we have the affinity between nodes and attributes. So that complicates the problem a lot. Since we have two different types of affinities, intuitively we're going to have two different affinity matrices. So which one should we be factorizing? Furthermore, if you think about the definition of PPR, or personalized PageRank, you can see that it's really just defined for the affinity between nodes. So how can we actually extend it to incorporate attribute information in the graph? So the way that we address this problem in our solution is as follows. First, we extend the notion of random walk to the case when we have attributes in the graph. So we defined what we call a node to attribute random walk, which starts from a node and ends at an attribute. And the idea is pretty simple. Starting from a node U, we just do a random walk as in the case of an attribute graph. But then at the end point, we're going to do one more step. We're going to look at the attributes that are associated with that node. Okay, let's say V. And then we're going to sample the attributes associated with V. Okay, and for each attribute, the probability of sampling it will be proportional to the weight between V and R. All right. So in other words, if there is a stronger association between the nodes and the attribute, then there's a higher probability that the attribute will be picked. Okay, so this is a simple extension to have a random walk that starts from a node U and ends at an attribute R. And the basic idea is that this kind of random walk can help us sample an attribute in the vicinity of the starting nodes. And if the nodes in the starting nodes vicinity all have a strong association with a certain attribute, then intuitively that attribute should have a strong affinity with the starting node. So that is the intuition that we have in this kind of random walks. But we do not directly use the probability that we have in this kind of random walk to model the node to attribute affinity. Instead, we do a little bit of normalization. And the intuition is as follows. If you think about the attributes of the nodes, it's kind of like words in a document. So if a word appears a lot of times in a certain document, then it could be representative of that document. But it also depends on how common that word is in the other documents, right? So if a word appears a lot of times in all of the documents, then it's not really representative of any document at all. Similarly, if we consider the probability of starting from a node U and ending at an attribute R, then even if this probability is large, it may not indicate a high affinity between the node and the attribute. Because if we start from some other nodes, V, and we still have a high probability to end up with this attribute R, then it indicates that this attribute R just has a strong association with every node. Okay, so in that case, there should not be a high affinity between the node and the attribute. So that's why in our formulation of this node to attribute affinity, we actually do a bit of normalization based on the relative strength of the association. And we also apply some logs and some constants to make sure that the resulting value is something within a reasonable range. So that's how we formulate the affinity from nodes to attribute in our approach. Okay, now what about the affinity from nodes to node? A straightforward solution would be to apply the kind of random walk that we had in the non-attributed graph and do it in the same way. But that's not what we did in our solution. Instead, we define a notion of random walk that starts from an attribute and end at a node. Okay, so it's a reverse type of random walk with respect to the previous random walk that we discussed. And then we combine the random walk from node to attribute and the random walk from attribute to node to indirectly model the affinity from one node to another. So in particular, if we have a random walk from a node U to an attribute R, and then we have another random walk from this attribute R to a node V, then intuitively, these two random walks would form an extending walk from U to V. Just that somewhere in between, there is a teleport from one node to another via a common attribute R that they have. And intuitively, this kind of random walk can help us model node-to-node affinity in an indirect manner. And why do we consider this type of extended random walk instead of just a direct random walk without attribute from one node to another? The intuition here is that we want to take into account attribute informations when we formulate the affinity from one node to another. Okay. Otherwise, if we just ignore the attribute information, then the node-to-node affinity will be solely decided by the graph topology. And that is not going to be good. And we have some indication in our experimental result in this aspect. Okay, so since we have some random walks from attribute to node, we also formulate an affinity of attribute to node based on a similar formulation that we had previously about node to attribute affinity. And then once we have these two notions of affinity, we can model the node-to-node affinity by combining these two affinity measures. So to compute the affinity from one node to another, we just take the affinity from the starting node to some attribute and then multiply with the affinity from that attribute to the target node. And we take the sum over all the possible attributes that connect these two nodes. So that would be our node-to-node affinity. Okay, so the way that we construct our embedding is as follows. We first construct the two affinity matrix. The first one is for node to attribute, and the other one is for attribute to node. And then based on these two affinity matrix, we'll construct two embedding matrices for the nodes in a way that is similar to our non-attributed graph approach. And then we'll also construct one embedding matrix for the attributes. And our objective is to ensure that if we take the first node embedding matrix and multiply it with the attribute embedding matrix, then the end result is something that approximates the node to attribute affinity matrix. Furthermore, if we take the attribute embedding matrix and multiply it with the second node embedding matrix, then we want the end results to be approximation of the attribute to node affinity matrix. And the way that we obtain these embedding matrix is to jointly factorize these two affinity matrices F and B. Okay, so we factorize it in such a way that the two factorization will share the same Y. So that is the intuition of our approach. And we have several optimizations to reduce space and time, which I'll omit here. So in our experiments, we use a variety of data sets with up to 59 million nodes and almost a billion edges. And we compared our solution, which is called PAIN for attributed graph embedding, with our previous solution for non-attributed graph embedding, as well as 9 state-of-the-art approaches. So 6 of them are based on neural networks, while the other 3 are based on factorizations and some other approaches. And the default embedding dimensionality is still 128. And by default, all methods would use a single thread. So these are the results that we have for node classification. So you can observe that the best performing methods in all cases is these two methods, which is the single thread version of our method, as well as the 10-thread version of our method. The 10-thread version is slightly worse than the single thread version because in order to facilitate parallel computing, we need to do some approximation in our computation, and that degrades the quality of the embedding a little bit. Meanwhile, the other approaches are all outperformed by our method, sometimes by a large margin. And on the largest graph that we have, there are only 4 methods that manage to produce embedding without running out of time or running out of memory. So that includes the 2 variants of our attributed embedding approach, as well as our non-attributed embedding approach, NRP, as well as a solution that uses NRP as well as the attributes of the nodes for node classification. So the approach that uses both the NRP and the attribute information has much better results than NRP itself. And that's intuitive because if we're going to classify the label of each node, apparently we can't just look at the topology of the graph. The attribute of the nodes definitely helps. But even if we combine NRP with attribute information, it's still not as good as our attribute embedding approach. And the intention here is that sometimes the attribute of the nodes in your vicinity would help the classifier to do a classification about yourself. Okay, it's like saying your neighbor in some way defines who you are. So since our attribute embedding approach takes into account the attributes in the vicinity of each node, it can get better results for node classification. Okay, so among the existing methods, the only 2 approaches that manage to scale to relatively large graphs are DGI and STNE. But in terms of the accuracy of node classification, it's much worse than our methods. And here we have the results for link prediction. And you can see that our attributed graph embedding approach achieved the best results in almost all cases. The only case in which we lose is this Google Plus graph. And the method that outperforms us is our unattributed graph embedding approach. So this sort of indicates that on this Google Plus graph, using only the graph topology is good enough for link prediction. On the other graph, this NRP approach actually performs much worse than our attributed embedding. So that intuitively means that when we do link prediction on attributed graphs, it's necessary to look at the attributes of the nodes instead of just the graph topology. So this also explains why in our embedding construction method, we actually consider the random walk from node to attribute and then the random walk from attribute to node instead of directly considering the random walk from node to node. Our last set of experiments focuses on efficiency. So as you can see here, the single thread version of our algorithm runs around 10 times faster than the best performing existing methods, which will be DGI. Meanwhile, the 10-thread version of our algorithm is roughly 10 times faster than the single thread version, which is intuitive. So in summary, our work demonstrates that it is possible to derive effective network embeddings without expensive neural network training. And the way that we did it is to use personalized PageRank or its variants to model the affinity between nodes or between a node and an attribute. And we use matrix factorization to derive embeddings while avoiding the usage of neural networks. Last but not least, I would like to acknowledge my co-authors of the 2 papers which this talk is based upon. And so they are Ren Chi, Jieming, Ying, Junchen, and Saraf. And if you're interested in the implementation of our algorithms, you may refer to Ren's GitHub, which is here. With this, I conclude my talk, and I'm ready to take questions.
Thanks very much, Xiaokui, for the wonderful talk. So now we might want to take a few questions from the audience since we still have some time. Jamie, go ahead.
Hello.
Hi.
All right. So thanks for the interesting talk. It's good to see that personalized PageRank is alive and well, even in the neuro-dominated landscape of today. My question is sort of at a high level, node embeddings for graphs are useful for multiple downstream tasks, right?
Mm-hmm.
In here, you built a node embedding and only demonstrated its effectiveness on one particular task, essentially a recommendation task. So can you talk a little bit more about that? Does this way of constructing node embeddings generalize to help other downstream tasks at all?
So here we consider the link predictions and node classification, because those are the two tasks that that are used very commonly in the literature to evaluate the performance of network embedding. So we haven't really think about other tasks as well. So which task would you recommend to evaluate the effectiveness of network embedding?
So I think the broader motivation here is that a lot of this comes from a lot of the work in node embeddings comes from the natural language processing community, right? And so there, contextual embeddings from BERT that say have proven to be effective for nearly all downstream tasks that you can think of. Regression, sentiment analysis, natural language inference, summarization, question answering, document retrieval, yada, yada, yada. And I think this is, more beyond than just your particular talk. One thing that I haven't seen in more in the KDD community and the community of people that work on graphs is this similar generality in being able to create build node embeddings that are broadly useful. So I was wondering if you have any thoughts on that.
Okay. Yeah. Yeah, I think this is something that the community need to work on. So right now, you're right. So usually people just focus on a small number of tasks such as link prediction and node classification, and there's no demonstration of the kind of generality that we just mentioned, like those embeddings that you can have from BERT. Yeah, I don't think I have a good answer to this question. So probably there will be more applications of graph embeddings in the future, so that we can demonstrate more generality. But at this moment of time, I think people still need to work on that.
Okay, thank you.
Thanks.
Thanks, Xiaokui. Thanks, Jamie. Anyone else have a question? If not, I probably will ask some just clarification questions for some experiments. Yeah, it's really wonderful to see so many comparisons with the baselines. I just have a question about the NRP methods. I can, from the slide itself, I can understand how the performance get really boosted up compared to the other baselines, but the accuracy seems also very good. Could you give us some more insights on why the NRP methods can do so much better than other baselines without giving so much performance improvements?
Sure. So intuitively, personalized PageRank is actually quite good a metric for graph affinity. And if you think about it, even the existing approach are kind of using something similar. Like even for deep walk, they are just considering whether two nodes appeared closely in a random walks. And in some sense, that's also, in a way, kind of similar to what personalized PageRank is doing, trying to identify nodes that you can reach frequently in random walk, right? So that sort of indicates that at the end of the day, many of the existing approach are doing some similar stuff. They are using something that is either similar to personalized PageRank or just a variant of it. But the way that I train the embedding is to generate a lot of samples, okay, and then try to optimize certain loss function. Whereas here, NRP is doing it in a more direct manner. We just do a very accurate approximation of personalized PageRank and then factorize the matrix. So I think it's fair to say that we can get better approximation of personalized PageRank. So intuitively, that's why we get better performance in terms of link prediction and no classification.
Thanks, Xiaokui. That's very clear. I have another question regarding the, I think it's the approximate methods. It seems like you're doing pretty, it's not very comparable as NRP for edge prediction task, but for node classification, it seems quite comparable. Could you explain why so? Like,
comparable? Sorry.
Comparable to the NRP method. There are two methods. One is the NRP, one is approximate PRP. I can't remember the name.
Approximate PRP. Oh, okay. All right.
Yeah.
So the intuition is that when we fit the embedding vector into the classifier and ask for classification, we actually normalize the embedding vector. Okay, before the classification is being done. And since we are just multiplying the embedding vector with a constant, after normalization, the two methods become equivalent. So that's why there, in terms of no classification, the result is pretty much the same. But for link prediction, there is no such normalization going on. So that's why for link prediction, the result is very different.
Right, got it. That makes sense. All right. Yeah, any other question from the audience? I think we're almost like at 10:30. If you have any questions, we can like our email to Xiaokui afterwards, or yeah, we're going to have conference Sigma So, like hopefully we can meet each other during the conference and shoot him questions. Is there any
Sure.
follow-up work along this line? Like what is the next thing for this week?
So we are also looking into graph neural networks to see whether there is a way to sort of accelerate it without any degradation of accuracy or something like that.
Sounds good. Great. Thanks again very much for the wonderful talk, Xiaokui, and hope to see you soon.